Hey everybody, it's Jenny from Norman S. Wright. A few weeks ago in my pumping systems video, I mentioned distributed pumping and I said I'd get back to it, so I want to talk about that today. So let's get started. Distributed pumping is a system that uses distributed secondary circulators located near each air handling unit or fan coil to provide localized pumping pressure and adjust water flow to meet load demands. At the end of the last video on variable primary flow, I mentioned that there are various control and balancing valves throughout the system to control the coils and the bypass. So let's move this up and let's pull up the drawing from last week. I drew in the bypass control valve, but not the other ones, so let's add them in here. There would be a control valve and a balancing valve after each coil. I don't have a lot of room, so we'll just squeeze this in like this. Dynamic flow control of the system is done by opening and closing these valves. You would use a differential pressure sensor at or near the furthest load to make sure there's enough pressure to supply that coil. So let's say in my drawing these are floors 1, 2, and 3. You might put the differential pressure sensor here, and your pumps would work to maintain pressure at this point. And then the control of the other coils will be handled by modulating the valves. So let's move this up and make some room. There's a pressure drop across these valves. I did a video a while back on valve authority. I'll link it below, but here's a quick refresher. Valve authority is the measure of how much control a valve has over the flow through the coil compared to the rest of the piping circuit. It tells you how effectively a valve can regulate flow. If a valve has high authority, it can precisely control the amount of water going through the coil. If it has low authority, there'll be little change in water flow until the valve actually closes. Let's move this up a little bit. Imagine putting a lot of water through a very large pipe. You would have to move the valve to almost close before it can affect the flow of water, and it'd be hard to get precise control with that valve. ASHRAE recommends a valve authority of 50 to 70%. But when you think about that, for every foot of head needed to move water through the piping, coil, and fittings, excluding the valve, the control valve must add an additional 1 to 2.3 feet of head loss to reach this level of authority. That means that your pumps will need to generate 100 to 230% more head than the base system alone to maintain that high level of controllability. Valve authority equals pressure drop across the valve when wide open, divided by the pressure drop across the valve when wide open, plus the pressure drop across the rest of the system. So if we look at this, we would have 1 divided by 1 plus 1 is 50%, or 2.3 divided by 2.3 plus 1 is 70%. So your pumps would need to operate at 2 to 3.3 feet of head for every foot of head required by the system minus the valves. That's a lot of extra pump energy. Let's move this over. Distributed pumping replaces these control valves with intelligent pumps. These smart pumps automatically balance the system by delivering the exact flow and precise pressure only when and where it's needed. With this decentralized pumping, you get increased occupant comfort and an energy-efficient pump system that is always balanced. So let's move this up and let me draw this. So we'd still have our primary pumps and chillers, and then on the secondary side, we'll have the coils and the distributed pumps with an integrated controller in place of the control and balance valves. And then let's draw in the piping and the decoupler. I didn't draw in all the valves in the previous drawings, but all of these systems would have a check valve to prevent any backflow from the coil that's not in use, and that would still be in here. The smart pumps would be controlled by a temperature sensor so they can adjust the flow as the load changes. Control of the primary pumps is based on temperature. There are 4 temperature sensors, 2 on each side of the decoupler. The primary pump control will be set up so that there is no flow through the decoupler when there is sufficient cooling. If the delta T on the load side, T4 minus T3, is the same as the delta T on the chiller side, T1 minus T2, then there'll be no flow through the decoupler. This means that the chilled water flow matches the required flow to handle the load. The controls are basically set up to maintain a 0 delta T between the supply and return on both sides of the decoupler. The system will be in perfect balance without excess flow to the chillers. This results in optimal chiller performance and avoids low delta T syndrome. Let's make some room. The controller should protect the chiller from low flow by using differential pressure sensors or a flow sensor. The benefits of distributed pumping is that it's self-balancing. You have improved chiller delta T, lower pump horsepower, and reduced pump energy because you remove the pressure drop associated with the valves. Pump energy savings have been seen to be 50 to 80% over a conventional system. Let's pull all this back on screen. So that's how distributed pumping works. As always, if you have any questions about whether distributed pumping is good for your application, you can contact your Norman Wright salesperson. If you have any questions or suggestions for future videos, put them in the comments below. Don't forget to like and subscribe to our YouTube channel. Thanks for watching, and I'll see you next week.